Welcome back again. This is Larry Benko, W0QE. This video is a follow-on video to the previous video on harmonics, where we basically looked at how we could get SimSmith to generate a voltage that would be appropriate to apply to say a filter or some circuit. And to use this example, this is just a blank SimSmith file. If I put a circuit in here, and we know that all these circuits, when they come up, the blank circuit is a do-nothing circuit. But that's okay. For purposes of discussion right now, the previous video dealt with the signals on this side, the generator. We would generate a signal of certain amplitude and certain harmonics. This video is going to deal with the load side. On the load, we'd like to be able to create a range of impedances that would stress the circuit that we wish to test here to the level we think is appropriate. That might be a whole bunch of impedances that represent less than 2 to 1 SWRs. They may represent less than 5 to 1 SWRs. It doesn't matter. It depends on what the application is. To date, I have always done this by taking a piece of transmission line, and this is an artificial piece of transmission line. I make it lossless so that we don't get any spiraling on our rotation. And pretty much I set, let's say this is a 3 to 1 circle right now here shown. This 3 to 1 right here is this dotted line. Let's say I could start off here with a 3 to 1 impedance. It doesn't matter what impedance it is. And let's turn that off for a minute. I'm right here. And I get a rotation due to my piece of transmission line. If I make my transmission line long enough, that's a little too long. Say right about there. That's a little bit more than rotation. So if we go from 0 to 32.9 feet, we will have traversed all the possible 3 to 1 SWR impedances. 150 plus J0, 16.66 plus J0. Up here we see 30 plus J40. Down here we see 30 minus J, I didn't quite get there, but 30 minus J40 basically. We can get them all. So if we wanted to use this as the load, this point right here from T1 to ground as the load, what we would do is we would not sweep frequency. We would sweep the length of our transmission line, and we would sweep it from 0 to, say, 32.9 feet. And 100 points is more than adequate. We'd sweep it, and there's our rotation. So, what's wrong with doing this? And the answer is probably nothing, although it's a little bit, it's only using those impedances. What about impedances in here? Wouldn't we like to face our circuit with all those impedances also? And over time, I got myself convinced that an impedance out here on the outside edge of my maximum desired range of impedances would be the worst case for my components here. Not any one particular impedance on this point, on this circle, would be the worst for all the components, but a point on this circle would be the worst for some component, and vice versa, a different point for different component, etc. However, we can do a lot better than that with SimSmith. This still may be true, and it still may be the easiest way to do it. But for the moment, I started experimenting with making SimSmith produce a bunch of fairly fairly equally spaced impedances throughout the Smith chart. I did this, and I engaged Ward with what I had done, and he proceeded to get back to me about a day later with a couple files. And the way he had done this was vastly superior to how I had done it. So I thought I'd share what he had done, which is kind of amazing, actually. It works very, very nicely. This is still a very good way of doing it for a lot of cases. But it's not nearly as clever as what he had done. So the first file he sent me was, it wasn't this file exactly, it was a variation. You're going to find this file to be pretty laborious to go through, and it is. But basically what we do here is we calculate a point in the center of the Smith chart, then we calculate a certain number of points a certain distance away, and then a larger number of points on another circle a certain distance away, and a larger number again, and a larger number again. In this case right here, I have 6 points per revolution at the beginning. I have 12 points here, 18 here, and 24 points in this circle. I go from the center point 1-to-1 SWR up to 1,000-to-1 SWR, and that gives me a total of 60 points. And we can change these values. If these don't represent enough points that we would want to use, we can say let's make it 8 circles. That's excuse me. That's considerably more number of points, and they're still all reasonably spaced. They're much more evenly spaced than what I'd come up with. And when I do this, that turns out to be 216 points. If I really only want my points to go out to a 3-to-1 SWR, I can put 3-to-1 SWR here. I should put 3-to-1 SWR down here too to prove it. And there we are again. Very nicely spaced group of impedances that fit in a 3-to-1 circle. This program has got this little nomenclature here, and I left it from what Ward sent me where it said slow. This executes slowly. It's so slowly that it's not very convenient to use. However, it has one point that's very nice, and that is we can take this slow calculation, that we get the results from, we can save it to a file, we can load it for use later, and when we load it later, it runs fast because we're not calculating all these points. So take a look at this just for a minute here real quickly, and we ultimately take the impedance that's over here, which is 0, I in an F block, and we add to it the impedance that we calculate here, and that gives us our new impedance. So the impedance at F1 here is our new effective load. We also have a few lines in the plot command here, which basically, well, this command right here just plots the dots we saw there. But we're going to write a file. We write it by putting the specifiers in the plot command window, but we execute that by doing file, write plot result files, and it brings up a window, and we name some file, and we save it. And when we save that file, we get a data file. Let me bring a data file up. Let me bring the one up actually that goes with this particular case here. So we look at this file. It goes from 0 to 216, so it's 217 points, and it's a combined list of gamma, the real part of gamma, and the imaginary part of gamma. Effectively 0 and 0, which is our first point right here. Then these continue on, and they're all values of gamma, the real and imaginary part of gamma. When we bring those in, we can convert those to impedances. But this is what the file is. So this becomes a two-part process. Part one is we create these files. And the reason this was a large SWR originally when I did this was because we'll create it this way, and when we bring it in, we'll scale it down if we want to scale it down. This lets me build a certain number of files. And I've built various files. I built about 5 or 6 with different numbers on them here, and we could build a file that had maybe say 10 points and 10 circles. It's more points. We could do whatever you want to do, but we'd save these and we use them later. So let's continue on now. We've generated the files, and the files that I've generated I will include in the link down below the video. You can click on the link and you can get all the files that are used in this video, including the generator file and the files that read the resulting data files. Okay, got an error here, and this is due to the fact that I moved the directory here. And here are the data files that I created. We'll load this data file. And all this stuff is built up to the next video that's going to happen. So let's just get rid of all this. Okay, no errors now. We've loaded our file. As I indicated in the last video, this right here, if you hover over here, we see up here in the view window what's actually in there. That's really a nice feature. If you're not familiar with that, people complain about the windows being too small to see in SimSmith, and you can't always make the window large because if you have too many components in a circuit, that just doesn't work. So let's look at this code. What we do here is if you load a file, you need to put an endpoint. You need to put the right endpoint in here. It tells you how many data points you're going to read. We're loading a file that has 216 data points. And we scale the SWR. That's a scale factor, so we take the big plot and we scale it down to the desired SWR. And what we do is we take remember all these points were gamma, and we take gamma, which is a complex number. The arc gamma is a function that converts complex number to impedance, and we put it here in a component which we call R, but it's a component that really doesn't matter. It's just it's a component that has a complex number in it, and we add it to this impedance, just like we did when we created the generator before. Now our impedances right here are all these values, and the beauty of this is really kind of clever. If I plot this, but if I also turn this on, I see a path. So each one of these points now has a value. Notice that we're sweeping right now. We're sweeping from, I should have mentioned this earlier too, we're sweeping from 0 to component N1, the end value, in steps of 1. So that's why we see steps of 1 here going along. So our first data point occurs for a 1-to-1 SWR. Our next 6 data points, that's point 1, point 2, 3, 4, 5, 6, all occur for a 1.13 to 1 SWR. Then the next points, 7, 8, 9, 10, 11, 12, up to 0.18, which is 1.27 to 1.28 to 1 SWRs. Then again and again and again and again. So this is kind of cute. As we increase the point reference, which is this number right here, and by the way, our circle here indicates this value right here. As I move this up, I'm moving up by 10 there. Let's move it up by 1. We can see it move along. So just like everything else in SimSmith, we want to highlight it. We can highlight it by using the value here, and we can see it. So let's look now with a generator. This generator is running 1500 watts. It's a UZ0 type generator. Let's go to the chart, square chart here, and let's look at the power output. And we don't want to look at the power output into L because L is 0 ohms. That's why we have 0 down here. We want to look at the power output into N1. N1 is our new load point. And look at this. This is way cool. Maybe I'm the only person who thinks this is cool, but nevertheless, I think it's cool. So what we see is we see one data point right here where we have 1.5 kilowatts into this point, into this node right here. Then we see, and let me move my so 0.1, 2, 3, 4, 5, 6. Those are the first 6 on the first SWR. That was 1.13 to 1. So let's plot SWR at the same time here. We see SWR stepping up. We see the power dropping. This is power due to mismatch loss. This is SWR. The beauty of this kind of a scheme didn't register with me immediately, but after using it in the final result, it's very cool. If I want to only look at a certain value of SWRs, I don't sweep all the way up to here anymore. If I only cared about SWRs up through, say, 1.9 to 1, I would stop at, is that 89 or that's 90? Let's see what point, where we need to be there. It's 0.90. I would just stop at 0.90 here. So I'd go to this point right here, and instead of stopping there, I'd stop at 90. And there I'd be. So if I was to calculate component stresses and values in here, I would only have to look at them here. So I would in the next video after this, what we're going to do is I'm going to build a filter here, and we're going to monitor the voltages, and we can look at the voltages with any amount of load variance we want to look at, and we can see the maximum voltages and currents we have here. And if you ask the question, gee, I really want to know the how tough to build my filter if I expect to see a 4 to 1 SWR, 5 to 1 SWR, I could very easily do that, and all I'd have to do is just change this value right here. So this is just incredibly cool, and this is a really nice feature. Now, if you didn't appreciate this feature enough to begin with, the interesting thing is this is frequency dependent. There's nothing in here that depends on frequency. It's a gamma value. The gamma value has nothing to do with frequency. We bring it in, we call it a point data, and this is why this is a little bit weird. If we were to try to bring this data into a file right here, this file expects to see a frequency response in terms of, and as a function of impedance. So the first item is frequency, and then you get a value for R and X. But we don't want frequency in there. I have done some stuff similar to this where I tried to put it in here and to no avail. And this is just a very, 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 very clever way of doing it. So I think I'll stop right now and begin to do the final video. But the final video will use this feature. And again, this feature can be used for anything you want to analyze at any point in time. And hopefully by the time you see the next video, you'll see the utility in doing all this. Thank you again, and it's been enjoyable doing another video.